In learning about open and adaptive systems, our team began to perform experiments regarding double skin facades and stack effect ventilation in our live models when simulating natural airflow ventilation around and within our proposed designs. Our compiled work in this video shows our documented results that measure this crucial and visible environmental factor, a process of design reiteration we engaged and explored throughout this semester.
The key terms and principles we looked at when exploring this project were stack effect, convection air movement, climate, wind-induced ventilation, flow path, and finally, Bernoulli's principle. The materials used to perform this process was a water table, 3D printed models, and food coloring. The water table, we used a phone stand as well as some lights to perform. Food coloring we would mix into a bucket when performing to add to the materials, and 3D printers we would make prints and send.
For water table operation setup, we would place the model into the water tank and adhere the surface as needed, fill the water tank to the level of water barely above the surface of the 3D model, and mix food coloring in a bucket of water. To perform the test, we would pour the food coloring into the tank and observe the air movement and flow path. And to clean up, we would empty the filling tank by pulling the plug, rinsing out the food coloring off the table in the tank, and dry out and restart the setup process for the next model. Stack effect is an effect that occurs with natural heat transfer. The warm air has a lower density than the cold air, so the warm air will rise to the upper part of the building, chimney, towers, etc. In testing stack effect, we looked at 3 different dimensions of floor plates for our tests. These tests and the way that they were modeled were somewhat unsuccessful due to the fact that when put in the live model, they performed more like cross ventilation. This is because the scale of the models and the pressure difference of the reservoir in the model base, the colored water was pulled through too quickly to show stack effect. Additionally, stack effect may have been hard to observe due to the lack of openings in the central atrium, again due to working at this scale.
Due to these testings, we decided to take a look at some real-world examples that implement the same strategy. So the first one we looked at for stack effect was Tel Aviv University. We just wanted to do a couple basic understanding of the building, looking at images, plans, sections, to really understand what the design intent was for this stack effect within this. And this building is located in a climate zone of CSA, which is warm temperature, steppe, and hot summer climate, or it's also known as a hot summer Mediterranean climate. As you can see, the architects did a study to look at what stack effect would look like within this building, so we wanted to see how it actually played out. So that was what we started to do. When looking at the model, you can start to see we're only testing from one direction, but you can see how the floors are sloped, and that starts to aid in the process of pulling this wind through and up through then this large atrium that they have located. You can see that it moves to the right as intended and moves up. But the one thing we started to notice is that they have an elevator core there right next to this atrium that really would stop this cross ventilation that they're striving for. So it was interesting to see how it actually starts to accurately play out what they wanted and intended to do.
Double skin facades utilize airflow through the intermediate cavity that can occur naturally or be mechanically driven. The 2 glass layers may include sun protection devices.
The first test shows this being completely closed off, where it shows that wind would not enter into the building, so you would not get this cooling/heating effect that could occur with a double skin facade. The second test begins to show this in a partially open state to where the air can circulate up and through and start to warm or cool the space, but not actually enter into the building, not creating that same effect, but it would go through this channel and then out the top. Third and final test shows how it can look where these would be open. When testing this, we noticed though that a lot of our openings aren't big enough because of the scale we're working at, and it leads to a limited effect of actual visibility, seeing the stack effect play out. One other factor could be the lack of difference in air temperature, because stack effect plays on the fact that a space would be heated or cooled on the inside, helping aid in this movement of air through this exterior channel and into the space. We then again looked at another real world building, this time the Cambridge Public Library here in Boston. You can see a couple images on the screen, and then we started to try and understand the climate and also the wind in this area, but the climate in this is a CFA, which is a warm, temperate, fully humid, hot summer climate according to the Köppen classification system. When observing this test, we began to notice that initially that we had some interference at the top from the food coloring immediately rushing up and over, leading to some obscure results that could occur. But in addition to that, you still can see the double skin facade working as intended. It enters in through this bottom channel that would be in the ground and starts to come up and through and exiting out through the first window. It takes more time to get to the second story window, but then you do eventually see it start to make its way up there slowly and surely. After our observations made from these initial tests, we decided to take a look at combining these two strategies together. We wanted to see what would happen if we had a double skin facade as well as a stack effect system taking place beyond. So the main goal of our design test then was to take a deep dive into what this could look like. This design test was performed in Massachusetts, and learning from our previous iterations, we tried to implement a ground floor plane to start to limit the amount of overflow of water that would come up and over these models. So that seemed to be successful in this test, which was good to see. When observing this, you can see how the double skin facade stops that initial flow of air movement and channels it down to that bottom channel and then up through the building. It immediately enters into those spaces, which is great to see. And then having that opening in the top of the wall allows that stack effect to then also work in coordination with the double skin facade. So this starts to prove that these two systems can work together and how they could start to actually be a successful method. The one thing we did notice is on the second floor, for some reason, there seemed to be a lack of movement to the stack, and don't know exactly why that may be happening. That could be due to temperature differences that we're not actually showing because we have the consistent temperature of water, but eventually it does at the very end start to pull into the stack, but it wasn't as strong of a movement as we expected to see.
Overall, throughout the semester, working in these live models has been an engaging and insightful process for us to learn about and test natural ventilation concepts, the difficulties presented by the live models, and our struggles with what we have expected to see from what we learn about adaptive systems versus what we have the ability to test in our live models is with the scalability and the fact that it is testing one concept at one moment in time.
Some of these issues, again, relate to scale and how these models don't actually operate and function at such a small scale. It leads to some issues when actually trying to view these, which is something that could be addressed in the future. In future testing, it would be more beneficial to put this more in a box, quote unquote, to have the ability to limit the amount of overlap that happens above and below the models. Also, it would be interesting to start to see how these play out in these larger scale moments, and that could be done in a multitude of ways, but something that should be explored.